We'll be having a very short class. I'll try to finish off early. Okay, thank you. Thanks for that. We are marked 1, 1, G1, G3, G1. Then from 3 to 5, from 3 to 4, there is another block which is parallel to G3. Okay, so please observe the direction of flow of signal. It is towards the output. So from 3 to 4, there is a G2, okay, which is parallel to G3. Should be very careful about the direction of flow of signal in the block diagram. Then again from 5 to 6, there is a block minus H1, which is a feedback. It's not H1, it's minus H1. Then from 6 to 2, we have another feedback. Okay. Then from 1 to 6, we have another forward block, which is G4. So minus H2 for the feedback, then minus H1 is for the feedback, and G4. So is it correct? Or anything is missed? So one thing is, arrow mark should be drawn here, which indicates flow of signal from 5 to 6 with a gain of minus H1, and there should be minus G4 because this sign is negative, therefore this should be minus G4. So what I would like to highlight here is that you should copy the sign as it is. Okay, copy the signs as it is and the direction of flow of signal as it is. So one may ask me the question, how come G4, which is a transfer function or which may be the transfer function of Planck, can be negative? So you don't bother about that. Whatever the question is given, whatever the sign is given, just copy and keep it as it is. So this should be minus G4. So those who are looking at this carefully or writing this note, please make those corrections. So I'm skipping the discussion part about what mistake has been done and all because you correct it yourself because it's not that relevant to the syllabus. The next is find the forward path, find the closed loops, then find the applying the Mason's gear formula. So let us look at the forward path quickly. So one signal is flowing from 1, 2, 3, 4, 5 towards output. So how to identify this loop is with respect to its gain. So I'll tell the first forward path 1, 1, G1, G3, 1, 1. Second forward path 1, 1, G1, G2, 1, 1. Third forward path 1, minus G4, minus H2, G1, G3, 1, 1. Third forward path is done. Then the fourth one is 1. Okay, gain is 1, then minus G4, minus H2, G1, G2, 1, 1. So there are only 4 possible forward paths. Now look at the closed loops. So one closed loop starts from node 2. So 2 means G1, G3, 1, minus H1, minus H2. One closed loop. And the closed loop is G1, G2, 1, minus H1, minus H2. So only 2 closed loops are possible. There isn't any closed loop starting from 1 because the signal flow is towards this direction. You cannot take this as a closed loop. Okay. The third closed loop is not possible. Only 2 are possible. So this is Mason's gain formula. Since there are 4 forward paths, k is equal to 1, 2, 3, 4. So let me write P1, first forward path, G1, G3, second forward path, G1, G2, third forward path is minus G4, minus H2, together it will become plus. So plus G4, H2, then G1, G3, and the last option is G4, minus H2, together it will become plus G4, H2, then G1, G2. So I hope this should be clear to everyone. Next, let us write the loop gains. Okay, this isn't visible. So the loop gains, please look at the diagram. The loop gains are G1, G3 in the forward path and minus H1, minus H2. Okay, so first closed loop is in this path. It is G1, G3, minus H1, minus H2. So first closed loop gain. Second closed loop gain is G1, G2, minus H1, minus H2. Okay, g1, g2 minus h1 minus h2. Next, let us determine the determinant of graph. So delta is equal to 1 minus summation of loop gains. The summation I said, it is very simple. Just add up all the gains. So just for the sake of simplicity, I have written summation of loop gains as L1 and L2. So it is 1 minus L1 and L2. Then how to find delta K? So I say delta K is quite confusing. I repeat the definition of delta K again. So if you want to find delta K, remove all those gains from delta which are touching the kth forward path. I repeat, remove all those gains from delta which are touching kth forward path. So that will give you delta K. So how you are supposed to read delta 1? So delta 1 is obtained by removing those loop gains which are touching the first forward path. Okay. So you have delta here and you have forward path here. Okay. So first forward path is what? This forward path. Okay. So to get delta 1, I have to remove those loop gains which are touching this forward path. Okay. So my straight question is whether L1 loop 1 is touching this forward path? Obviously. So what we say touching here is they have a common node. Loop 1 is having a common node and P1 is also having some common node. So they are touching. So to find delta 1, I will remove L1 here. Okay. Then my L2, which is this one, loop 2 is this one. Whether L2 is also touching the first forward path? Of course, even if there is a single common node, it means as good as they are touching each other.
Sir, which is L2 again? Can you repeat?
L2 is G1, G2, 1 minus H1 minus H2. Is it clear? Okay, L1 is G1, G3, 1 minus H1 minus H2. Fine. So what I mean to say is both L1 and L2 are touching the first forward path. Okay, both L1 and L2 are touching first forward path. So let us remove L1 and L2 from delta to get delta 1. So what will be our delta 1? Can anyone tell me the answer?
Once.
It is 1. Without any doubt, it is 1. Okay. So similarly, can you try for delta 2? Anyone try for delta 2? I'll give some time, just a quick calculation. So for delta 2, look at the second forward path. So for delta 2, if you look at the second forward path in the diagram, okay. So our second path is G1, G2, 1, 1. Fine. This is the second path. 1, 1, G1, G2, then 1, 1. So one can easily again say that both L1 and L2 are touching the second forward path also. Okay. So since they are touching the second forward path, our delta 2 is also 1 minus 0. So similarly, if you look for delta 3 and delta 4, you will end up with 1, 1, 1, 1. Right? So that's it. It's very simple. You can look at this diagram later. What will be our final Mason's-Gain formula? It is summation of Pk delta K divided by delta, which ends up with P1 delta 1 plus P2 delta 2 plus P3 delta 3 plus P4 delta 4. Very simple. We have P1, P2, P3, P4, delta 1, delta 2, delta 3, delta 4 here, and the determinant delta here. So how it looks like? Very simple. Just go on filling everything. G1, G2 into 1 is, sorry, G1, G3 into 1 is G1, G3. Then G1, G2 into delta 2, which is G1, G2 plus G4, H2, G1, G3 plus G4, H2, G1, G2 whole divided by determinant, which is 1 minus G4, sorry, G1, G3, H1, H2. Fine. Delta is this one. I am just filling the L1. Fine. Then the L2 part is G1, G2, H1, H2. So this is our overall transfer function. Okay. So the signal flow graph technique is quite easier compared to the block diagram reduction technique, which I had told in the previous class. The block diagram reduction technique will adapt replacing each blocks with certain simplification steps. Fine. But that block diagram reduction technique is only useful when the diagram is simple. Okay, where you have a direct closed loop diagrams and you can replace it directly with a closed loop transfer function. But here we don't have any simple diagram. We have a different kind of a diagram. We don't have any simple closed loops here. So shifting to SFT is quite useful. Fine. So any clarification, any doubts here? So that's it about the first unit. And I repeat, except the modeling of electrical circuits, I have finished everything. You can go through the syllabus. Except the modeling of electric circuits, I have finished everything. So we started with mechanical translation system, then mechanical rotational system, then analogous systems, force voltage, force current, then torque voltage, torque current analogy. So I say torque voltage, torque current are similar. Okay, so just a small modification is required. And apart from this, we studied about basic understanding of control system. We studied about what is positive feedback, negative feedback, and we studied what is open loop control system, closed loop control system. Okay, then we understood what is the necessity of mathematical modeling. Okay, why it is necessary to study the mathematical modeling. So all those things are completed. Fine. So why I'm like keeping the electrical circuits pending is it's not so difficult as we think. Like mechanical system, we already have studied RLC circuits, and you know how to write the differential equation with respect to RLC. That's why I'm keeping pending, and I will finish it quickly. Once we study time response, I mean the first part of next unit, we have to reiterate the electrical circuit part. So then I will just give a brief examples about the electrical circuits, the transfer function or mathematical modeling of electrical circuits. So we have done mathematical modeling. Okay, specifically in the unit 1, we have done the mathematical modeling, which includes say translation mechanical system as well as block diagram and SFG representation. So mechanical system mathematical model, if you know what is the next step, I mean what is the next step after understanding the mathematical model is the question. Fine, I repeat, our objective is to understand what next we need to proceed after understanding mathematical modeling. And what are the drawbacks if you don't understand the mathematical modeling. So that's the thing we need to understand. So the flow goes like this. Suppose imagine asked to you are asked to develop a controller algorithm for a drone or a quadcopter system, or even for an aeroplane. You are asked to develop a control algorithm. So you cannot directly start coding for a controller. First, you need to understand what that actual system is, what all parameters it has. Does it has friction? Whether quadcopter or a drone has a friction? Yes, of course. Maybe very less, but a friction. So what are those friction? Is it a like I mean conventional friction what we understood in translation system, or is it a friction what we understood in a rotational system, or what kind of friction? That you have to sort out. So one may say that the rotate propellers, I mean the rotors, which are basically the motors we are using, will obviously have friction. Okay, but I mean very less as compared to other scenario. But can we ignore that very less friction to get a accurate control? So all those things will come under mathematical modeling part. Fine. So the precision what you are expecting depends on whether to consider the friction or to ignore the friction. And then comes say weight of the drone. You cannot ignore the weight of drone. To design a controller, you need to consider it. So mass will come into picture. Fine. Then where is the spring effect? Spring effect. If you want to include a spring effect in the drone modeling, how does it affect? Okay. Then comes air drag, gravitational force, all those things will come into picture in mathematical modeling. So next, after understanding only, you can proceed. Okay, I have understood the system now, let me design controller. So before designing the controller, again, there are few more intermediate steps that you need to understand. So what are those? intermediate steps that we will jump on to unit 2 now to understand it. So unit 2 is time response of the system. So just let me show you the syllabus.